Now I'm going to turn to the partially linear model, which is an example of a semi-parametric model, and I'm going to show two ways of estimating it. The partially linear model, in this model, the conditionally expected value of y conditional on x and z is x beta plus h of z. So there's a linear part, it's linear in x, but it's nonlinear in z. It's an extremely powerful tool to use in practice because you can say, I want to understand the nonlinear relationship between one of my regressors and my outcome, and I want to control for a bunch of other things where I just want them taken care of, and I'm fine with just doing that in a linear way. The problem is that kernel regression does not permit us to include this, so we need to do something clever. And the solution is to use the Frischwell-Lovell theorem. The approach here is called the Robinson double residual method. So this is our model where the conditional expectation of epsilon conditional on x and z is 0. So the trick that we use is first to take expectations only conditioning on z on both sides of the inequality. Then we subtract these two equations from each other. And the trick here, of course, is that this thing here, the expectation of that conditional on z, is just this thing. Because when we condition on z, it's no longer stochastic, it's just a number. So when we subtract the two, we get y minus its expected value conditional on z, which we can think of as y regressed on z. We get x beta minus x regressed on z beta. This thing dies out, and then we have a new error term. And so this gives us a linear equation where we can regress y tilde, which is y minus y regressed on z, on x tilde, and that will give us consistent estimates of beta. And we do that by simple good old OLS, where x tilde has all of the x's where they have been subtracted x regressed on z. So the next idea is simply, and to do that, we do these regressions by kernel regression. We want these expected value of x given z and the expected value of y given z, the ones up here, sorry, we want those to be completely non-parametric, so we use a kernel regression there. Finally, we can obtain the h function by doing a kernel regression on y minus x beta, so we move this thing over on the other side, and then since we have beta hat, we can compute this thing and construct this y minus x beta, and on the right hand side only h remains. So by regressing this residual on z using kernel regression, we can obtain h. An alternative way of doing this, instead of using the Robinson double residual, is although we can use sieves here. So instead of using kernel regression in this step and kernel regression in this step, we can use sieve non-parametric regression. But we can also do it in a single step with sieve regression. The idea is this: pick a dimension d and some basis functions, for example polynomials. Then we treat the model as if it were fully parametric. In other words, when we implement this, we just add our basis functions of z, which could be 1, z, z squared, z cubed, and so on. And we just include those as additional regressors together with x. So we have our x, and then the P matrix contains, for example, polynomial of order d in z. And then we just regress this whole thing on y using the OLS formula, and the first coefficients coming out are going to be our beta hat, and the last coefficients coming out are going to be alpha hat. This is what happens. If we look at the red, the black line is the true function. So the red line gets too far down here and too far up here because there's correlation between x and z. So it doesn't If we just do this non-parametrically, we don't take into account the correlation between x and z, and we incorrectly attribute the whole thing to z. But as you can see, both the two-step kernel and the two-step Sieve estimator get closer to the true relationship. From this graph, it looks like the Sieve does a little bit better, perhaps, than the kernel. The kernel has some trouble here.